Good morning. So I just got a message from Mr. TK. He says that the test is tomorrow. So test 2 is this Friday. That's tomorrow, the 22nd of October at 5 p.m. So he said that if you are writing at the centers, please notify the centers today so that they can make arrangements. Okay, because even though we send the papers to all the centers, some centers are not used. So you have to tell them that I will be coming tomorrow. So the paper will be sent to all the centers, but you must tell them that you are definitely coming to write there, because it's not that every center is used during every test that we have. So they should know that you are coming to write there. Okay, so Friday, 5 p.m. please be there on time. It'll be pretty much a similar test to the one we wrote last week. Open book, same content. Okay, so today I just wanted us to finish off on this chapter of matrices, looking at eigenvalues and eigenvectors. It shouldn't be a very long class. Then you can go and finish preparing for tomorrow's test. Okay, so one thing that we should note is that whenever we get the eigenvalues and the eigenvectors that correspond to the eigenvalues, these are linearly independent. Okay, so we should note that the eigenvectors of the different eigenvalues these are linearly independent. Okay, so what that means is that one is not a scalar multiple of the other, so you cannot multiply one eigenvector by some constant and then you get the second value that is associated, second eigenvector that is associated with another eigenvalue. Okay, so let's say I have my eigenvectors. Let's say this is x1, x2, and x3. Okay, so if I have k1, x1, so that means I multiply the first eigenvector by a constant, the second one, k2, by a constant, and k3 times x3, and then this gives me the 0 column vector. Then because they are linearly independent, this means that k1 plus k1 is equal to k2 is equal to k3, and this is equal to 0. So it is not possible to find constants here that are different from 0 so that when you add these, you get the 0 column vector. Okay, so we did one question here. Let me see if I can find it. Okay. Yeah. Let me just write it down. We had this one. This was our first example. A is equal to 2, 1, 4, and 5. And we then got our eigenvalues. We said lambda is equal to 6. And lambda is equal to 1. So these were our two eigenvalues. And then we had eigenvectors associated with each of them. So the first one was 1, 1, the usual one. So this was 1, 1. And then with the other one, our usual eigenvector was -4 and 1. So this is one question that we worked out already. Now we want to show that these eigenvectors are linearly independent. So what we would do, so this, I'll call it my x1 corresponding to lambda 1, then lambda 2 corresponding to x2. Okay, so what we want to do is solve this system k1 x1 plus k2 x2 is equal to the 0 matrix. So we have this, if we were to write this in matrix form, this would be k1 times 1, and here we also have k1 plus k2 times -4, which is just -4k, 2, and then k2 times 1, and this is equal to our 0 matrix. This is a 0. Okay, so we know how to add two matrices together. So we would have k1 -4 k2, k1 plus k2. This is equal to 0, 0. And then this would lead to the system of linear equations, which is k1 -4 k2 is equal to 0, and then k1 plus k2 is equal to 0. So we want to show that these two eigenvectors, this one and that one, are linearly independent. And the way we show that is by showing that this variable here is 0, and then that variable over there is equal to 0. So we can then write the augmented matrix. So we have 1 -4, 0, and then 1, 1, and 0. And then we perform Gauss elimination. So here with this row, we can make this one a 0. So we can see that row 2 minus row 1 will give us a 0 where we want it. So we just say row 2 minus row 1. And then we have 1 -4 is a 0. Then 1 minus 1 is 0. Then 1 minus -4, this is 5, and that's a 0. Then if we look at this, you can see we have 5k2 is equal to 0. This will mean that k2 is 0. So we have 5k2 is 0, or we can just divide this by 5. But from here we can clearly see that 5k2 is 0. This means that k2 is 0. Okay, and if we know that k2 is 0, we can always substitute in there and then work it out. So we have k1 minus 4, k2 is equal to 0. So I have k1 minus 0 is equal to 0. This means that k1 is also equal to 0. So I've shown that it doesn't matter what variables I multiply, not variables, what constants I multiply the eigenvalues, eigenvectors with, they are linearly independent, because the only way for this equation here to be equal to 0 is if my constants here are equal to 0. So this, when you show that those constants k1, k2 are equal to 0, then you have shown that the two eigenvectors are linearly independent. Okay, so that's what we want to show when we are saying that the two eigenvectors are linearly independent. So look at the questions in exercise 6.4, and we'll see how many of those we can do. Then if we finish before time, then just go and prepare for tomorrow's test. Let's see, exercise 6.4. Question 1 says, determine the eigenvalues and their associated family of eigenvectors. So this is exercise 6.4. Start with number 1. Now 1.1, we have this matrix here. We have 3, 2, 2, and 3. So we need A minus lambda I. So that means we subtract lambda here and subtract lambda there. So we will have 3 minus lambda 2, 2, and then 3 minus lambda. Then the determinant of this matrix must be equal to 0. So we have 3 minus lambda squared minus 4. This is equal to 0. So here, very easy to solve. We don't need to multiply out the brackets. Just take the 4 to the other side. So we have 3 minus lambda squared is equal to 4. Then plus or minus the square root on both sides. 3 minus lambda is equal to plus or minus 2. This means that lambda is equal to 3 plus or minus 2. Lambda is equal to 5, or lambda is equal to 1. So those are my two eigenvalues. Then I will substitute both of them here and then work out my bases, and then the non-basic variable I will equate to A or B, and then come up with a family of eigenvectors. So let me just squeeze it here. So when lambda is equal to 5, what I have is 3 minus 5, which is minus 2. and then 2, then 2 here, and 3 minus 2, this is minus 2, and remember this is the augmented matrix. So you can see I can divide this first row by -2. Just say divide by -2. And then here I can just say row 2 plus row 1. So this last one I just say row 2 plus row 1. Okay, then what I get is 1 minus 1, 0. And -2 plus 2, or 2 plus -2 is 0. And then -2 plus 2 is 0. And then 0 plus 0 is just 0. Okay, so you can see now that my basis will have only one of the variables, whether it's x1 or x2, and as always you can pick whichever one you want, because this column vector is the same as that one. So if I want to make this one a 1, I will just divide the row by -1. Then I can say this is my unique column, unit column matrix. Okay, so usually just pick the first one. So we have our basis, which is x1, and then we let x2 equal to a. So we let x2 equal to a, where a is just a real number. Okay, so if x2 is a, so I have x1 minus a is equal to 0. So x1 minus a is equal to 0. This means that x1 is equal to a. Then my family of eigenvectors will be here. x1 is a, x2 is a, so it's just a, and then the usual one, the one that we call usual, this is when a is equal to 1, will look like this 1, 1. Okay, that's the eigenvector associated with lambda equal to 5. Then we do the same thing when lambda is equal to 1. So with our matrix here, we'll substitute 1. So we have 3 minus 1, and over here we have 3 minus 1. This will give us 2, 2, 2, 2, and we have 0 here, 0 there. So this row we will divide it by 2, and then here we will say row 2 minus row 1. Okay, this gives us 1, 1, 0. Then 2 minus 2 is 0, 2 minus 2 is 0, 0 minus 0 is 0. Then here again, you can pick your basis. So basis will be x1, and then you let x2 equal to b. So looking at this, I have x1 plus b is equal to 0. So I have x1 plus b is equal to 0. This means that x1 is equal to minus b. So the family, this will be minus b, and B, and then the usual, this is -1 and 1. And you can always check and see that these two are linearly independent. Then let's look at number 2, say 2.1. 2.1, we have this matrix here, 2, 1, 0, 1, 2, 1, 0, 1, 2. Okay, so we want A minus lambda. So this will give us 2 minus lambda, 1, 0, then 1, 2 minus lambda, then 1, 0, 1, and then 2 minus lambda. Okay, then we need the determinant of this matrix and then equate it to 0. So the determinant, this is 2 minus lambda multiplied by 2 minus lambda times 2 minus lambda minus, so here we said remove the row that it is in, the column that it is in, you're left with this matrix here, and the determinant of this matrix is just this minus that. Then the second one is negative because we have plus, minus, plus, minus, plus, minus, and so on. So you can use whatever row or column you wanted to work out the determinant. It doesn't always have to be the first one. Okay, and usually it's a good idea to use the row or column with the most zeros. Okay, so with the second one, it's -1. So I remove the row and the column that it is in. I have 1 times this. So I have 2 minus lambda minus 0. And then the last one is positive 0 times whatever the determinant here is, which is just 0. Okay, and this determinant must be equal to 0. So what we have is 2 minus lambda cubed minus 2 minus lambda minus 2 minus lambda. This is equal to 0. Okay, so this is 2 minus lambda to the power of 3 minus 2. 2 minus lambda is equal to 0. Then you can factor out 2 minus lambda. And we have 2 minus lambda squared minus 2 is equal to 0. And then multiply this out and simplify. So you can see first we'll have this is equal to 0, and then again here we don't even need to multiply, we just equate it to 0. So we have 2 minus lambda is equal to 0, or 2 minus lambda squared minus 2 is equal to 0. So for the first one, we have lambda is 2. For the second one, we have 2 minus lambda squared is equal to 2. This means that 2 minus lambda is equal to plus or minus the square root of 2. And here lambda is equal to 2 plus or minus the square root of 2. So I have my three eigenvalues. There's 2 plus the square root of 2, and then 2 minus the square root of 2. So we start with lambda 1 when lambda is 2. So our matrix here, we have 2 minus 2, 2 minus 2, 2 minus 2. So it's zeros along the mean diagonal. So I have 0, 1, 0, 1, 0, 1, 0, 1, 0, and then on this side I have 0, 0, 0. Okay, then the only thing is here, if I look at this, I can see clearly that x2 is equal to 0 because it's the only one in the row that's 1, and then on the other side I have 0. So here x2 is equal to 0. Same thing with the last row, I can see that x2 is equal to 0. And then my two unit column matrices, column vectors, it's this one here and that one there, but you can see because the position of the ones are the same, it means I need to choose one of them. So my basis is going to be x1. So if that is x1, then let x3 equal to a, which is just any real number. And then I can see here that x1 plus a is 0. So x1 plus a is 0. And this means that x1 is equal to minus a. Then I come up with my family of eigenvectors. So x1 is minus a, x2 is 0, and then x3 is a. This is the family, and then the usual when a is equal to 1. This is minus 1, 0, and 1. Okay, then I would do the same thing when lambda is 2 plus the square root of 2. So this is lambda 2, just 2 plus the square root of 2, and then substitute it into your matrix. So 2 minus 2 plus square root of 2, this is minus square root of 2, 1, 0. We have 0 here. And then we have 1 minus the square root of 2, 1, 0, 0, 1 minus the square root of 2, 0. So here we need to perform some row operations. So we can start with seeing what will be the easiest thing to do. Okay, we can make this one here a 0. And say that row 1 plus square root of 2 times row 2. Okay, so negative square root of 2 plus positive square root of 2, this is 0. And then we have 1 plus negative, so it will just be 1 minus square root of 2 times square root of 2, which is 1 minus 2. 1 minus 2 is negative 1. And then 0 plus square root of 2 is square root of 2. So 0 here. And then second row, I'll leave it as it is for now. Okay, then I see that I can make this one here a 0 just by adding row 3 to row 1. So here, say row 3, row 1 plus row 3. So 0 plus 0, minus 1 plus 1. Square root of 2 plus negative square root of 2, 0 plus 0, and then my second row has not changed, third row has not changed. Okay, then I can make this one here a 0. So this is row 2 plus the square root of 2 times row 3. This is 0, 0, 0, 0, and then 1 plus 0, minus square root of 2 plus square root of 2, then 1 minus 2, and then this is 0. Then this one has not changed, so this is 0, 1, and then minus the square root of 2, and that is 0. Okay, so here it is not obvious that any of the variables are 0, so we can't tell for sure that any of them are zeros, and it is not possible to make another, if I make a 1 there, it changes that one, and same thing over here. If I make this one here a 0, by combining it with this row, it'll change this value here. So this is where I stop. So I can see that I have two column vectors. There's this one and that one, and the ones are in different places. So I can say that my basis is x1 and x2, and then we let x3 equal to a, sorry, not a, I should use b because the first eigenvector had a's, so this one I use b just to distinguish them. Okay, and then from here I can see that I have x1 minus b is equal to 0, And then here I have x2 minus square root of 2b is equal to 0. I have x1 minus b is equal to 0. So this means that x1 is equal to b. And then I have x2 minus square root of 2. So x2 minus square root of 2b is equal to 0. And this means that x2 is equal to the square root of 2 times b. So then my family of eigenvectors will be x1 is b, x2 square root of 2b, and x3 is b. And then our usual is when b is equal to 1, this is 1 square root of 2 and 1. Okay, and then we do the same thing with the third eigenvalue. So here lambda 3 is equal to 2 minus the square root of 2. So our matrix is going to be square root of 2, 1, 0. So we have 0. Then 1 square root of 2, 1, 0, 0, 1 square root of 2, 0. So again, the same thing. We try and get as many column vectors as possible. Okay, so we can make this one here as 0. We'll say square root of 2 times row 2 minus row 1. This will give us square root of 2 minus square root of 2, or rather square root of 2 minus square root of 2. And then this is 2. Let's first finish. Sorry, the first row is not changing. So square root of 2, 1, 0, 0. Now the second row, the one that is changing, square root of 2 minus square root of 2. This is 0. Square root of 2 times square root of 2 is 2 minus 1. This is 1. And then square root of 2 minus 0. This is square root of 2. And this is 0. And then we have 0, 1, square root of 2, 0. Then row 3, I can say row 3 minus row 2. So here you can see I'll have 0, 0. The first row does not change. Square root of 2, 1, 0, 0. Second row, 0, 1, square root of 2, 0. And here I'll have 0, 0, and 0. Okay, then I can make this one here as 0. And I say row 1 minus row 2. Square root of 2 minus 0, 1 minus 1 is 0. 0 minus 0 minus square root of 2 is minus square root of 2. And then 0 minus 0 is 0. And the second row has not changed. This is 0, 1, square root of 2, 0, and then 0, 0, 0, and 0. Then here we can divide by square root of 2. 1, 0, minus 1, 0, 1, square root of 2, 0, 0, 0, 0, 0, 0, like that. So again, you can see I have these two that are in the bases. So my bases will be x1 and x2, and then we let x3 equal to c, which is some real number. Then here I have x1 minus c is 0. So this means that x1 is equal to c. And then from the second row, I have x2 plus the square root of 2c is 0. This means that x2 is equal to minus square root of 2c. So the family of eigenvectors, this will be c minus the square root of 2c, and then c, and then the usual is 1 minus the square root of 2, and then 1. Okay, so those are your solutions with the 3 eigenvectors. Then number 3, number 3 says determine all the eigenvalues associated with this matrix, and then show that they are linearly independent. So our matrix is 2, 1, 0, 1, 1, 1, 0, 1, 2, and then we have 2 minus lambda, 1, 0, 1, 1 minus lambda, 1, 0, 1, 2 minus lambda. And then we work out the determinant of this matrix and equate it to 0. So it's 2 minus lambda multiplied by 1 minus lambda, 2 minus lambda, minus 1, minus, here we will have 0, no, it'll be 2 minus lambda minus 0. So it's just minus 2 minus lambda. And then the last one will be 0 times that, which is just 0. And this is equal to 0. So again, here you can see 2 minus lambda is a common factor. So I factorize that. So I have 2 minus lambda. I have 1 minus lambda, 2 minus lambda, minus 1. This is equal to 0. So 2 minus lambda is equal to 0. Or 1 minus lambda, 2 minus lambda, minus 1 is 0. Okay, then this means lambda is equal to 2. And with the second one, I have to simplify it. I will get minus 3 lambda plus lambda squared is equal to 0. So this means lambda minus 3 plus lambda is 0. So lambda is 0 or lambda is 3. So those are my 3 eigenvalues, 2, 0, and 3. So this, now I work them out. Let me start with when lambda 1 is 0. So my augmented matrix will be 2, 1, 0, 1, 1, 1, 0, 1, 2, and then 0, 0, 0. Okay, so I already have a 0 here. We can make a 0 even here, why not? So we say that row 1 minus 2 times row 2. So this is 0. Then 1 minus 2 is minus 1. Then 0 minus 2 is minus 2. Then this is 0. Then 1, 1, 1, 0, 0, 1, 2, 0. Then here I can just say row 3 plus row 1. And then this one here divided by minus 1. I have 0, 1, 2, 0, 1, 1, 1, 0, and then 0, 0, 0, 0. Okay. Then I can make this one a 0, say, sorry, this one here is 0. I say row 2 minus row 1. 0, 1, 2, 0. And then 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 2 is minus 1, 0, and okay, so from here I can see my bases, x1 and x2. So we let x3 equal to a, and then we have x1 plus 2a is equal to 0. Then we can solve for okay, I think I made a mistake here. Is that right? 1, 0, 1, 2. Oh, okay, no, it's fine. This is x2, so it's x2 plus 2 a is equal to 0. Okay, so from the first one I have x2 plus 2a is equal to 0. So this means that x2 is equal to minus 2a. And then we have x1 minus a is equal to 0. This means that x1 is equal to a. So the family we have a minus 2a and then a. Then the usual we have 1 minus 2 1. Then lambda 2 equal to 2. We have 0, 1, 0, 1 minus 1, 1, 0, 1, 0, 0, 0, 0. Okay, we can make a 0 here, just say row 3 minus row 1. And here we can also make a 0 and say row 2 minus row 1. So we have 0, 1, 0. 1 minus 0 plus here minus 1 plus 1, then 1 plus 0, 0, and this is just 0, 0, 0, 0. So here clearly x2 is equal to 0. See, x2 is equal to 0, and these two have 1s in the same position, so our basis will only be made up of one of them. So this is x1, and then x3 is equal to b. So here we have x1 plus b is equal to 0. So x1 plus b is equal to 0. This means x1 is equal to minus b. Then we can write down our family of eigen. So this is minus b, 0, b. And then the usual, this is minus 1, 0, and 1. Then when lambda is 3, this is x lambda 3, we have minus 1, 1, 0, 1, minus 2, 1, 0, and 0, 1, minus 1, 0. Okay, can divide this one by minus 1, and then say row 2 plus row 1. I have 1, minus 1, 0. This is 0, minus 1, 1, 0. And this is 0, 1, minus 1, 0. Say row 3 plus row 2. You'll see that here I have everything is equal to 0. This is 1, minus 1, 0, and 0. 0, 1, minus 1, 0, and 0, 0, 0, 0. Okay, so I can make a 0 here. just say row 1 plus row 2. One, 0, minus 1, and 0, 1, minus 1, 0, 0, 0, 0, 0. Okay, so our bases x1, x2, then we let x3 equal to c. So here we have x1 minus c is 0. This means that x1 is c. Then we have x2 minus c is 0. This means that x2 is equal to c. So our family of eigenvectors, this is c, 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 and the usual is 1, 1, 1, 0. And now the second part of this question was to show that these are linearly independent. So it says I've reached the maximum number of pages. Okay, let me just do that, save it, and then just show that working quickly. And then we're done with matrices, finally. Okay, then let's see, can make another one very quickly. So with this one here, what we need to do is we say that we need to show that they're linearly independent. So we have k1 times x1, k2 times x2, and then k3 times x3. This is equal to 0. Then from here, we need to show that k1, k2, and all of those are equal to 0. So doing that is not difficult. So we have k1. Our first one is 1 minus 2, 1. And then k2. This is minus 1, 0, and 1. Then k3. This is 1, 1, 1. This is equal to the 0 matrix. So we can come up with an augmented matrix. Before that, let me just write this. This will be K1 minus K2 plus K3 is 0 minus 2K1 plus 0 plus K3 is equal to 0. Then K1 plus K2 plus K3 is 0. Okay, now the augmented matrix. We have 1, minus 1, 1, 0, minus 2, 0, 1, 0, 1, 1, 1, 0. So we can say row 2 plus 2 times row 1, and then row 3 minus row 1. So this will give us 1, minus 1, 1, 0, and then 0, minus 2, 3, 0, then 0, 2, 0, 0. So here we can clearly see that K2 is 0. So here you can see K2 is 0 because we have 2, K2 is equal to 0. That means K2 is 0. Yeah, but we just continue. I'll say divide this by 2. And what else can I do? I can say row 1 plus 2 times row 3. Okay, let me just write that. So I have 1, minus 1, 1, 0. I have 0, 2, minus 3, 0, then 0, 1, 0, 0. Then say row 1 plus row 3. And then row 2 minus 2, row 3. Okay, this will give us 1, 0, 1, 0. And then 0, 0, minus 3, 0, 0, 1, 0, 0. Then divide this by minus 3. We get 1, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, 0. Then I can also make this one a 0. Row 1 minus row 2. Then you'll see I have 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 0, 0 here. Okay, so from here you can see K1 is 0, K3 is 0, and then K2 is 0. Okay, then when you've shown that all of these K's are equal to 0, then you would say that the eigenvectors are linearly independent. Okay, so that was the second part of the question. Oh, finally done. All right, so remember the test is tomorrow 5 p.m. If you're writing at the centers, you need to go to the centers and tell them that you will be coming to write there. Again, this is because the paper is sent to all the centers, but not all the centers are used. So there are some centers where we send the paper, but no student writes there. So obviously the people want to go home. It's Friday at 5 p.m. But if you tell them that that you are going to write there tomorrow 5 p.m., then somebody will be there to invigilate your test. So it is an open book, just like this one. Same content, probably, definitely. Okay, so we'll stop here finally, and we will then continue tomorrow.